So here we are back at it with Godot docs, getting started. Our first 3D game, moving the player with code. All right. Yesterday was my day off, and I was daydreaming a little bit about 3D games. Let's go. So it's time to code. We're going to, yeah, I'm sorry for saying that, honestly. But it was going to be a lot lamer than that, trust me. We're going to use the input actions we created in the last part to move the character. Awesome. So here's another note. For this project, we're going to be following the Godot naming conventions. GDScript, I forgot about this, so let's read it. Classes, nodes use Pascal case. Okay, the nodes are going to use Pascal case. Variables use snake case. Okay, constants use all caps. Yes, I remember that. We might get into this later, C#, depending on if we need more control, because that's what I hear the C# is for. Anyway, let's get into it. So we're going to right click the player node and select attach script to add a new script to it. Actually, you know what? I also, what's this? Anyway, I also had to get Windows 11, and they got this thing now where we can just do this. Let's do this. I want this, but on the other side. Come on now. There's not this, but the opposite way. I mean, like, this is cool. You know, this thing is cool, but also, where's this go? How do we do this? Okay, hold on. We do this here. Can we, is that a thing? I don't think we can do that. I don't think this thing squashes like that. Although it should. Oh, looky here. Looky here. Shablam. Awesome. Check us out. Looking cool. Except for... Okay, there wasn't a timeline there. All right, back to this. Okay, back to this. There we go. So, here we go. Right-click the player node and select Attach Script to add a new script to it. Attach Script. They do have that. Also, no. We're going to select Player, and we're going to grab this. We're going to do this Attach Script method. Although, let's go over here. Attach Script. Yeah, it doesn't have a hotkey. So let's just do let's do this thing, because that's what we learned in the first... in the 2D Godot. So let's click that. Here we are back here. Select attach script, and it's okay. In the pop-up, set the template to empty. Okay. Before pressing the create button. Okay, create. We set it to empty because we want to write our own code for player movement. Gotcha. All right, so create it. Although I kind of like the code they give us. We can kind of use it sometimes. I don't know. We'll see. So we did that. So let's start with the class's properties. We're going to define a movement speed, a fall acceleration. Hold on. We're going to define a movement speed, a fall acceleration representing gravity, and a velocity we're going to use to move the character. Awesome. So let's copy this and put this in the script. Let's just highlight this. Let's do a Control A here, Control V, and there we go. Can we knock this down? Yeah. Okay, cool. All right. So we got that, and let's come down here. So there are common properties for moving these are common properties for moving a body. Export var speed is 14. Export var fall acceleration is 75. Var target velocity equals velocity 3.0. pardon me, vector 3.0. Oh, we got a vector 3 when we're doing 3D. Instead of the vector 2. Interesting, right? I mean, obviously we would hit this, we would get to this part, but yes. And remember, the .0 just means it's going to set the vector 3 to 0, 0, 0, right? So these are the common properties for a moving body. Okay. The target velocity is a 3D vector. True. All right. Combining speed with a direction. Oh, okay. Here we define it as a property because we want to update and reuse its value across frames. I wonder how that's going to work. I am curious. This is going to be interesting, learning how to make things change directions and go in certain directions using 3D vectors. Okay. Note, the values are quite different from 2D code because distances are in meters. Okay, and not in pixels, I guess. While in 2D, 1,000 units pixels may only correspond to half of our screen's width. In 3D, it's a full kilometer. Turns out. But it's only a representation of a kilometer, obviously, you know. I mean, we could, if we went down, we could act like we went, and we went 14 kilometers per hour. We could act like we went in a direction 14 for 1 kilometer or whatever. But the thing is, we're not moving. It's just pixels on a screen being changed. You know what I'm saying? And then updated states, you know. Trust me. Remember, guys, this is not real. We're not dealing with reality here. The reality is these colors in their specific spots. That's what's reality. I don't know why I went on that rant. So let's code the movement. We start by calculating the input direction vector using the global input object in physics process. Okay. We start by calculating. Okay, let's just take it, drop it in, and see what this is. Physics process delta. Okay. We'll read this in a second. So we're going to create a local variable to store the input direction. All right. So var direction equals vector 3 is 0. So right now it's 0. I wonder. We're probably going to go into it, but I wonder what the three. I thought the three parameters were going to be X, Y, and Z, but I'm pretty sure now that one of them. I don't know. I don't know what it is. I don't know what it's going to be. Let's see. So next we check for each move input. So we check for each move input and update the direction accordingly. Okay. Direction.x plus 1. Okay, so we're changing the directions by pixel? Is that what we do? I don't know. So if is action press move right, we're going to change the direction by 1 unit. Maybe it's a meter. I don't know. 1 unit in the X direction. We're going to add to it. So move right. So going this way. Yeah, that's going to be plus. Okay. And also, if we keep moving right, it would go down too, and that's plus also. And then keep moving right, and that's going to be the opposite of this direction. So that's okay. I see. Now I kind of see why down is positive. A little bit, because this going right is positive. Then if you turn right again, it's going to be positive again, right? And then if you turn right again, it's going to be negative because it's the opposite of this. I just said that, and then if you turn right again, it's negative because it's the opposite of this. I guess that's how they got it. I don't know. Who knows? So then we got move left is going to be minus going that way, right? If input dot is action pressed, move back. Notice how we are working with the vectors x and y axes. In 3D, the XZ plane is the ground plane, okay? So if move back is pressed, we're going to say direction Z plus 1. Is that right? No, okay, so whatever I set up here, I don't know if that's true or not. But this, I guess if we press move back, direction Z plus 1. What? What? What does that mean? Oh, wait. What? Okay, so Y is going to be up and down. Z is the plane, is the plane, and X is which direction you're going on the plane, or which direction you're going in Y. I don't know. We'll see. We'll see. All right, let's keep going. So there's that. There's that. So we've got the move back is going to be Z plus 1, and move forward is going to be minus. That's wild. Anyway, so here we're going to make all calculations using the physics process. That's this thing. Okay. Virtual function. Like process, it allows us to update the node every frame. True. But it's designed specifically for physics related code, like moving a kinematic or rigid body. Okay. I guess, I mean, because we're gonna have to move the little trees and the little bushes and stuff. And that's just what I'm thinking we gotta make. We're gonna have to move the trees and we gotta learn Blender for real, because we gotta make our own trees and our own bushes, and we gotta make our own cats and dogs and all that stuff. Anyway, let's get to it. Blah. See also, to learn more about the difference between process and physics process, we can see this. I'm sure I think we'll get here at some point. It's bigger. Yeah, this is in the manual. We'll get to this if we need it, but for right now, let's just keep going. All right. So we've got that. This out of here. We start by initializing a direction variable to vector 30. Yeah, we just went over this. So we're right here. Then we checked if the player is pressing one or more of the move inputs and update the vectors X and Z components accordingly. Yeah, that's what X and Z accordingly. True. These correspond to the ground plane's axis. True. All right. These 4 conditions give us 8 possibilities, and 8 possible directions. Okay. So it's not by pixel, it's by specific direction, I guess. In case the player presses, say, both W and D simultaneously, the vector will have a length of about 1.4. But if they press a single key, it will have a length of 1, because that's the hypotenuse of, let's remember, it's the grid. We got all these boxes in the grid, right? We got something here? Yeah. No, that's not going to be. How do we see the graph? I don't know. All right. Oh, here we go. So we got these, right? So X and here's Y, here's X, right? And so this is the length of 1, this is the length of 1, and this is going to be the hypotenuse of this triangle, And we know this is a squared plus b squared equals c squared. And so the square root of c squared. So c is going to be the hypotenuse, which is 1.4. I don't remember. I don't know how to say it. I can just, write it on a piece of paper and turn it in. That's my experience with math. Stop looking at me. Stop looking at me. Anyway, there we go. So here we go. But if they press a single key, we want the vector's length to be consistent and not move faster diagonally. True. To do so, we can call its normalize method. True also. True also. So let's grab this while we're here. Why not? I mean, we're just giving it away, right? Let's drop it here on 26. Make sure to get it in line with these ifs and this stuff. Boom. Okay, so this is everything. This represents all this. So let's just see ya. Get out of here. All right, cool. Here, all right, let's look at it before we read about it. So we've got if direction does not equal vector 3, 0. If it's not a vector 3 with zeros in it, direction equals direction dot normalized. Setting the basis property will affect the rotation of the node. Pivot dot basis equals basis dot looking at direction. Well, we're going to have to read about this one. I have no idea what that says. Here we only normalize the vector if the direction has a length greater than 0, which means the player is pressing a direction key. Oh, if the vector, if there's, okay, so if, okay. So right now when it has nothing in it, it is 0, I guess that's what that means. And then if it has like a 1 in the first, second, or third position, it'll have a length. And so it's something, all right? I guess. We compute the direction the pivot is looking. What? We compute the direction the pivot is looking by creating a basis that looks in the direction. What? Okay. A 3x3 matrix for representing a 3D rotation and scale is what a basis is. The description is the basis built-in variant type is a 3x3 matrix. True. So, and then tic-tac-toe. Used to represent 3D rotation, scale, and shear. It's frequently used within a transform 3D. A basis is composed by 3 axis vectors, each representing a column of the matrix X, Y, and Z. Okay. The length of each axis, vector 3.length, influences the basis's scale, while the direction of all the axes influence the rotation. Usually these axes are perpendicular to one another. However, when we rotate any axis individually, the basis becomes sheared. Okay. Applying a shear basis to a 3D model will make the model appear distorted. Oh, man. Oh, it keeps going too. Look at this. Look at this. Let's do that first before we go. Wow, boy. What do we do? Do we go over basis or do we just say, okay? What is this basis though? A basis is orthogonal. A basis is orthogonal. What does that mean? If its axes are perpendicular to each other. What? Oh, geometric orthogonal describes lines, planes, or axes that intersect at right angles. Okay. Mathematical meaning. To vectors whose dot product, scale product, 0. Oh man. You know what? I think that this person that wrote this is just a little too mathy right now and forgot that we're not. So let's just keep going. We'll figure this out later. I don't remember what this is for though. What this means in Godot. What's this mean in GDScript? Yes. Yes. That's how we access pivot. Pivot is, let's make this bigger. No, let's not make this bigger. Pivot is, give me a second. Pivot is this. Okay, so that's how we access this right here. All right, so pivot.basis equals basis dot looking at direction. And direction is something we declare here. We'll hopefully when we see this in action, it'll like make sense fundamentally or whatever the word is. But right now we're gonna get back to it. See ya. So man. Then we're going to update the velocity. We have to calculate the ground velocity and the fall speed separately. We're going to be sure to go back one tab so the lines are inside the physics process button, but outside the condition we just wrote above. Hold on, man. What? What do you... What? Oh, I see. Okay, so let's take it from here, from this curly brace up to right here. Let's get that. Because this is this. All right, so let's drop it down 1, 2, bring it back 1, drop it like that. All right, so and then bring it back 1. We'll get it better next time, but that's what it's supposed to be like. Grab everything from either from here to here, or from or from here to here. Whatever you want to do. I like going backwards because it's, I don't know, I think it's easier. And then drop it in there. So there we go. Let's go to the next part. Let's actually look at this first. So we say target velocity dot x equals target velocity. Did we make that? Yeah, we did. Look, we did. Okay. So target velocity dot x. So if it's x, y, z, this is the first position. So this would be like target velocity at 0. But anyway, whatever. Target velocity dot x equals direction dot x times speed. Okay. Target velocity z equals direction dot z times speed. Okay. I mean, I can understand kind of what that means. Okay. Vertical velocity, if not, is on floor. And if in the air, fall towards the floor. Literally gravity. Literally. Anyway. Okay, target velocity dot y equals target velocity dot y minus fall acceleration times delta. I like that. It utilizes the delta so that we can get pretty constant frame rate, right? Shouldn't we have more deltas though? I don't know. Anyway, so we got that, and then moving the character. Velocity equals target velocity. Move and slide will be called as well. Did we call it? I think this is a thing that they're going to talk about. All right. Give me a second. I got to take a breath. I had to yawn. Oh, man. Take a breath, take a yawn. Take a stretch. Ooh. Oh, man. Learning. Learn something new every day, right? Especially if you're in a course. So there we go. And then we got move and slide, which we'll learn about in a little bit. So let's go over it over here. So the character body 3D dot is on floor. What? Okay, function returns true if the body collided with the floor in this frame. Okay. Okay. That's why we apply gravity to the player only while it's in the air. Okay, so it's always checking if it's on the floor. Is on floor is every single frame it's checking to see if the player's on the floor. Okay. Okay. I can get in. I can get in on that. Is that what we say these days? Anyway, so that's why we apply gravity. Okay. So for the vertical velocity, we subtract the fall acceleration multiplied by the delta time every frame. Yes. That would make sense, right? This line of code will cause our character to fall in every frame as long as it is not on or colliding with the floor. True. The physics engine can only detect interactions with walls, the floor, or other bodies during a given frame if movement and collisions happen. We're going to use this property later to code the jump. Okay. I mean, I can kind of understand a little bit. Not too much though. On the last line, yeah, right here, we call character body 3D dot move and slide. Okay, so that's what this is. Okay, so and then I guess that's so just what they're making sure we understand is that this is called on. Let's do this. Which one's character body 3D? This one. This one's called on the node that the script is on itself. If this move and slide was on pivot, it would be pivot dot move and slide, right? I think that's what they're trying to make sure we understand. All right, let's keep going. So character body 3D dot move and slide, which is a powerful method of the character body 3D class, true, that allows us to move a character smooth. Hold on, let me see. On the last line, we call character body 3D dot move and slide, which is a powerful method of the character body 3D class that allows us to move a character smoothly. If it hits a wall midway through a motion, the engine will try to smooth it out for us. Okay. That's cool, right? It uses the velocity value native to the character body 3D. Okay. Yeah. So it's like easy ease if you know anything, if you know about like After Effects and the other stuff. It's like a parabolic, metabolic, symptombolic, hyperbolic. I don't remember the word. The one where it's a exponential, but it goes down, and I don't remember. Anyway, it's that kind of curve out. Anyway, whatever. Yeah. And that's all the code we need to move the character on the floor. Shut up. Let's do a Control S. Let's run it. Huh? Oh, we haven't defined it. Okay, let's go back over here. Here's the complete player.gd code for reference. It should be the exact same as us. What we got? Ground velocity, vertical velocity, moving the character, and then this stuff. Yeah. just like us. We're so cool. Except where's, okay, if direction, no, that's there. Oh, this one doesn't have this these words in between. Okay, there we go. So let's go down some more. Testing our player movement. We're going to put our player in the main scene to test it. Okay, do we have a main scene? Yeah, we do right there. To do so, we need to instantiate the player and then add a camera. Unlike 2D, in 3D, we won't see anything if our viewport doesn't have a camera pointing at something. Okay. Important. We're going to save our player scene and open the main scene. We can click on the main tab at the top of the editor to do so. We will. Let's do Control S here. Player scene is done. Okay. Main. Let's main tab at the top of the thing. Okay. So if we close the scene before, head to the file system dock and double click it. Okay, we didn't do that. To instantiate the player, right click on the main node and select instantiate child scene. All right, so let's do this right here. We're over here. Click on the main node and then instantiate child scene. It's this thing right here. Okay, so click the little link right here. Now that we did that, in the pop-up, double-click player.text scene. Boom. Remember that? Yeah, I remember that. The character should appear in the center of the viewport. Let's go get this. Oh! Let's do a Control Z. Let's do a Control Y. Remember, it's not Control Shift Z with these guys. It's Control Y. Okay, great. Although we could change it to Control. We'll do that later. Another time, another chapter. I was on the Reddit for Blender the other day, and somebody was talking about he went like hours to change all of the key bindings to something he was used to in the pay version, like the Maya. Maya's like the paid Blender, but Blender's like really gaining a lot of ground. But anyway, and he said he took like hours to get it like just what he wanted. I was thinking maybe we're gonna have to do that one day too. So yeah, in the pop-up, we're gonna double click player.text scene. We already did that. The character should appear in the center of the viewport, and it does. Adding a camera. So let's add the camera next. Like we did with our player's pivot, we're going to create a basic rig. Okay. Let's see. What does that mean? They'll tell us. We're going to right click on the main node again and select add child node. Main node, we're going to right click main node and press Control A is what we're going to do. All right. Now we're going to do a marker 3D. Marker 3D right there. Boom. Now we got that, and name it camera pivot. Pivot. Remember the Godot naming convention? Pascal case for these, remember? Select camera pivot and add a child node camera 3D to it. All right, so this is selected. Control A. Do we got camera 3D over here? Not yet. Camera 3D right there. Cool. Our scene tree should look similar to this. It does. It looks exactly like that. Pardon me. So notice the preview checkbox that appears in the top left of the 3D view when we have the camera selected. Huh? This? Yes. We can click it to preview the in-game camera projection. Oh, that's terrible. Awesome. That's awesome, though. Look, that's awesome. I think it's great. We're getting somewhere. So we're going to use the pivot to rotate the camera. as if it was on a crane. Okay. Let's first split the 3D view to be able to freely navigate the scene and see what the camera sees. Okay. In the toolbar right above the viewport, okay, click on view, then 2 viewports. We can also press Control 2, whatever. Is this view? View. View. Yeah, look, there's the view. View, then 2 viewports. What is this? That's cool, right? I like it. It feels like we're in a drone looking down at a massive thing, or we're. Yeah, that's how I feel. Because look at all the dust in the distance, as if it was real life. What are we doing? All right, we did that. We got this. Yeah, we're cool now. Control 2, Control 1, Control 1, Control 1, Control 2, Control 3, Control 2, Control 3, Control 2. All right. So let's go. On the button view, we're going to select our camera 3D. Camera 3D. Button view. How do we know which one's what? On the button view. Bottom view. My bad. Sorry. On the bottom view, we're going to select our camera 3D and turn on the camera preview by selecting the checkbox. Okay, we're select in the bottom view. What? Hold on. Was that right? I don't think that was right. Man, I don't think I did that right. What is this? No. Control Y. Okay, what? Okay, so when I clicked this, what did it do? Oh, it went to message. Okay, so click this again. Okay, cool. All right, so yeah, that's what happens if you click outside of this thing. What it's doing is going in and checking something out. So if we click this, it's going to player. Click this, is doing that. Click outside of this, it's doing something else. Camera 3D, that's how we get back to it. Okay, cool. Anyway, so in the top view, okay, in the bottom view, select our camera 3D and turn on camera preview by clicking the checkbox. Okay, so this needs to be selected, and in the bottom one, preview. Okay. In the top view, make sure our camera 3D is selected and move the camera about 19 units on the Z axis. Drag the blue arrow. Here's the blue arrow. 19 units. Remember, it's probably going to show up right here. Yeah. How many was that? How many was that? No, that's 0 units. Okay, keep going. 19. Perfecto-ish. All right. I think that was 9. I think that was enough. So here's where the science happens. Magic. Shut up, bro. Select the camera pivot and rotate it negative 45 degrees. How do you do that? Around the x-axis using the red circle. This one? We'll see the camera move as if it was attached to a crane. Okay, so let's look at this. Maybe it'll go negative. Yeah, look. I guess. Oh, wait, hold on. Control Z, Control Z. All right, let's look down here while we're doing this. Okay, so look at the number here, but also look at this. I wasn't looking at this at all. That's what I'm saying. Okay. All right, cool. I wasn't looking at that at all. So we got 19. Sure, it doesn't matter. All right. And then camera pivot rotated 45 degrees. around the x-axis. Hold on. That wasn't... All right, camera 3D. Move it this way. 19. It's way over here. 45 degrees. Camera pivot, 45 degrees. Rotating. Negative 45 degrees. Oh, that's cool, actually. That's cool. I'm like staring at this, but now I can see this. I'll see this move when I'm editing. But yeah, that's cool. That's cool. That's real cool, actually. We're in business right now, huh? We're in business now. We have to figure out the exact way to... Oh, look at this. Here's this 45, negative 45. Let's go over to camera 3D, see if we can't hit transform to 19. Let's put this at 19. Exactly. Boom. So that's how we dial it in. Perfect. Okay. Let's go back. Let's look at this. All right, so we can run the scene by pressing F6 and press the arrow keys to move the character. Shut up. F6. Wait, whoa, what are you doing? Oh, look at us. Look at us go. Right off the map. I think we got to do that again. I don't care. Keep going. I hate we'll figure out how to actually because look, we'll figure out how to get smooth animations to where it looks like it's not just clipping straight to back forward. Where to look like that thing's actually turning around, right? You know what I'm saying? Where the character's actually turning around. I can already see it now. We have it when we push this. We give it a little tiny pause to give the animation a chance to go through, making it look like the character turned around, and then we make it start. Oh, nice. All right, we're in business. All right, let's go. All right. Take a breather. I'm going to take just a breath. Take a breather if you need it, because we're already at 43 minutes. I'm taking a breath. I'm doing a stretch. Let's go. All right. So we can see some empty space around the character due to the perspective projection. No. F6 over here, buddy. Let's put this here. All right. We can see some empty space around the character. What? Due to the perspective projection. In this game, we're going to use an orthographic projection instead to better frame the gameplay area and make it easier for the player to read distances. What are you talking about? Empty space around the character. What does that mean? What does that mean? All right. I don't know what that means. We're going to select the camera again in the inspector. Are we still going to have this playing? What? Anyway, let's get rid of this. All right. We're going to select the camera again in the inspector. Pardon me. We're going to set the projection to orthogonal. All right. Camera. We're already there. Projection, perspective. Now it's going to be orthogonal. Ooh, okay. And the size to 19. Size. 19. Oh, okay. The character should now look flatter and the ground should fill the background. Let's go F6. It do. Control Z, Control Z, F6. I liked it better this way, though. Honestly, I really do like it better this way. It feels like you're actually playing on a table instead of like this fake, stupid fake world that they're totally trying to convince you that this fake world is real. Anyway, I'm not. We'll get into my philosophies later. So there's that, and then let's do Control Y, Control Y, Control Y, Control Y, Control Y. All right, and press F6 again to see it go. Okay, it fell off the table. We couldn't see it though. All right, that's cool that we know how to do that now. Here's a note. When using an orthogonal camera in Godot 4, directional shadow quality is dependent on the camera's far value. Okay, the higher the far value, the further away the camera will be able to see. Okay. However, higher far values also decrease shadow quality as the shadow rendering has to cover a greater distance. Okay. If directional shadows look too blurry after switching to an orthogonal camera, decrease the camera's far property to a lower value such as 100. Okay. Don't decrease this far property too much, or objects in the distance will start disappearing. Far property. This one right here. So it's at 4,000 right here. We would decrease it to a lower value. I mean, isn't 3,900 changing it like that's the difference between 3,900? Isn't that actually a lot? I don't know what they're saying. Let's push F6 over here and see what we got. Does that look bad? Let's change the far to 100 and just see what it looks like. Camera, far to 100. F6. Does that look cooler? I mean, it looks a lot more questionable. Like the silhouette's a lot more questionable now, for sure. These guys, these characters, I bet you they did it on purpose. Let's do it again. No, shut up. Okay, you see, okay, so it was a lot more defined when we had the far closer. You saw the shape of it. All right, so there's that. We're going to test our scene, and we should be able to move in all 8 directions and not glitch to the floor. True, we already did that. Ultimately, we have both player movements and the view in place. So next we're going to work on the monsters. Awesome. All right, so there's the end of that. If you want to go through these user contributed notes, they got some. Shouldn't the camera pivot be attached to the player somehow? In this demo, the camera has a fixed position and covers the entire level, similar to mini games like Mario Party. Therefore, it doesn't need. This guy's wondering. This guy's just talking about first person versus third person, I think, or maybe something else, or maybe true third person and not fixed. I don't know. Anyway, so it doesn't matter because we don't have that problem. Let's go to the next one. All right. So now we're on to designing the mob scene, and we'll see you next time.